Experiment 4. Heat treatment of steels. Please refer to the practical guide for general comments, rules, and regulations, as well as the criteria required to successfully complete this experiment. Steel is an alloy consisting of two main alloying elements, namely iron and carbon. In the portion of the iron-carbon binary phase diagram that we will be dealing with, there are four important equilibrium phases that must be considered. These phases are delta ferrite, austenite, alpha ferrite, and cementite. An equilibrium phase is formed under conditions that allow the system to reach equilibrium. The most important of these conditions are the rate at which a material is cooled from high temperatures. Equilibrium cooling refers to a very slow cooling rate. This means that the material is given enough time to reach equilibrium at every point in the process of cooling down a material. If we consider a 1% carbon steel at 1100 degrees Celsius, we can see that under equilibrium cooling conditions, the phases that will form are as follows. At 1100 degrees Celsius, the material is fully austenitic, and there are no other phases present in the microstructure. As the material cools down to approximately 820 degrees Celsius, the material will enter the two-phase region where both austenite and cementite are stable at the same time. At this point, the first material will transform from austenite to cementite. As the temperature decreases even further, more austenite transforms to cementite until the temperature 738 degrees is reached. At any point below this, austenite is no longer stable, and the microstructure will transform to a mixture of alpha ferrite and cementite, known as pearlite. If the material does not cool under equilibrium cooling conditions, the equilibrium binary phase diagram will not necessarily yield correct results, and a time temperature transformation or TTT diagram must be used. These diagrams contain non-equilibrium phases that could form if the material is cooled down fast enough. Two non-equilibrium phases that exist are bayanite and martensite. The green line signals the start of the pearlite transformation at slower cooling rates. At higher cooling rates, the material may transform to bayanite. The bayanite transformation is shown by the blue line. At very high cooling rates, it is possible to form martensite. The martensite transformation start occurs along the black line labeled MS. Transformations are complete and no other transformations take place past the red line or the line labeled MF. Martensite is a very hard, brittle phase that forms in carbon steels if very high cooling rates are applied to the material. This occurs because at very high cooling rates, carbon does not have time to diffuse to more favorable positions in the microstructure. Therefore, the formation of martensite is a diffusionless process. It can be seen in this diagram that in order to form martensite, the material must be cooled down from approximately 780 degrees Celsius to approximately 550 degrees Celsius in less than 1 second, and then from 550 to 320 in another 9 seconds, as indicated in the diagram. A micrograph of martensite can be seen at the bottom left-hand side of the screen. Some important terms to be aware of during the practical can be seen on the screen now. For a hypoeutectoid carbon steel, the following will be true. If the material is austenitized and then annealed, the following microstructure will be seen. The material will become entirely austenite, and when cooled down slowly, alpha ferrite will start to form and grow in size until the temperature becomes so low that the austenite is no longer stable. At this point, the material will transform to a combination of alpha ferrite and cementite, which is known as pearlite. If the material is austenitized and quenched, an untempered martensite microstructure will develop. This microstructure resembles sharp needles of untempered martensite. If the material is then tempered, the martensite will become spheres of cementite in a matrix of alpha ferrite. This is known as tempered martensite. The objective of this practical is to determine the effects of cooling rates and subsequent heat treatments on the impact toughness of high carbon steel. Please pay close attention to the following practical demonstration. Several samples have been cut to size and placed in a furnace in order to be austenitized. Once the samples have been austenitized, they are rapidly quenched in water to produce untempered martensite. Half these samples are then temper heat treated to produce tempered martensite. The Sharpie impact tester makes use of a hammer to impact the sample and determine how much energy the sample absorbs in the process. In order to accurately determine energy absorbed, it is necessary to determine the energy lost in the system due to friction. This is achieved by performing the impact test without a sample in it. First, turn the needle to the 0 position. Then, press the lever to release the hammer and allow the hammer to perform at least one complete swing. This will generate a reading that corresponds to the energy lost in the system due to friction. Place the sample in the support and make sure the notch is facing away from the point of impact. Ensure that the needle is at the 0 position and release the hammer. This reading, minus the energy lost due to friction, is the energy absorbed by the sample. Ensure that you are taking readings from the outermost scale. The value must then be multiplied by 9.81 and divided by 2 in order to get a value in joules.